Well, let's start section 7.2. We're going to basically continue where we left off right here. So it's a really nice segue in the next section. You see, we just did a trigonometric integral, right?
Yeah.
And we did it with a reduction formula. What we're going to tackle now is, what if it's not just sine to the fourth power of x? What if it's sine to the fourth power x times cosine to the fourth power of x? Or something weird like that. Well, we're going to talk about that exact example, and I don't know if we're going to get there today, but we're going to talk about it eventually, probably next time, probably tomorrow, when we get back at it. We're going to see what happens in these cases when we have trigonometric functions being multiplied certain powers instead of our integrals. It's going to get kind of fun, it's going to get a little weird, going to get crazy, but we're going to have a good time with it. 7.2, we're going to talk about trig integrals. You know, the one we're going to start off with first is a very common one. We're going to start talking about what happens in your integrals when you have sine to a certain power and cosine to a certain power being multiplied together. So sine and cosine don't necessarily have to have the same power. They could, but I want you to consider the two cases that we have, okay? So here's two cases. Case number one. Case number one is the case where we have an odd power on at least one of these functions. So either m is odd, or n is odd, or both are odd. Do you guys, yeah, I know it sounds silly, but you know what odd means, yes?
Yes.
Odd is like 1, 3, 5, 7, 9, those powers. So case number one is where m and or n is odd. So they could both be odd. What's the only other case?
Even.
They're both even. Yeah. See, if one of them's odd, naturally the other one's going to be even. Hello. If they're both odd, none of them are going to be even. But if none of them are odd, they're both even. So m and n are even. Of course, I'm not going to leave you hanging. We're going to talk about both cases here. What I'm going to do for you, I'm going to give you the case by case to tell you exactly what to do first, and then we're going to follow those cases with a series of examples. Does that sound okay with you?
Yeah.
So let's talk about case one first. Case number one. Let's suppose, so case number one, either m is odd or n is odd, so either sine has an odd power or cosine has an odd power, or they both have an odd power. If sine has an odd power, if power of sine is odd, what we're going to do, we're going to strip off one of the sines. So that what that means is, like, if it's sine to the third power of x, we'd strip off one. We'd have sine squared times sine. Does that make sense? We're going to strip off one power. So we're going to keep one factor of sine. And then with the other one, you see, if we have an odd power of sine, and we take one sine away, we strip off that factor, then that odd power now becomes an even power, doesn't it? If it becomes an even power, we can do a couple things with it. We can, no, I'm sorry, not a couple things, we can do one thing with it. Then what we're going to do, so keep one factor sine, and use the Pythagorean identity to change sine squared x into 1 minus cosine squared x. You'll see why this happens, why this works in just a minute, why we're doing it. Okay, so If the power of sine is odd, no problem. Strip off one factor of sine, keep it. Use Pythagorean identity to change your even, the rest of the even, into this, using Pythagorean identity. If it's sine to the fourth, well, hopefully you can do something different with this. If not, you'd still do it. You'd have sine squared, and you'd still use this. Then you distribute. That would be a very long, tedious problem, which we're definitely going to get to. Yay! If it's the power of cosine that's odd, you do the same exact thing, only with cosine. Does that make sense? So, if power of cosine is odd, do this. Basically this for cosine. Now, what if they're both odd? What would you do if they're both odd? I don't know. Well, use the one that benefits you the most. For instance, pick the smallest power. Let's pick the one that gives you, hopefully, a sine squared or a cosine squared by itself. Does that make sense to you? So we use I'd say the smaller power, or use the power that's going to give you something squared. Okie dokie? So if both odd, pick the one that will give you a power 2, if you can. If possible. Okay, are you guys all okay with case 1? Probably not, actually, because we haven't even done an example. You don't even know what I'm talking about right now, except that we're going to be stripping off a sine or a cosine. You'll see it in a minute. Let's talk about case 2 first before we get to an example. I definitely want to do at least 2 of these things before we're done today. So case number 2. For case number 2. Let's say that both the powers of sine and cosine are even. If both powers are even, so cosine squared and sine squared, you've got both of them. What we're going to do is we're going to use our half angle formulas, and you're hopefully going to see why in just a minute. Use half angle formulas. Does anybody out there remember the half angle formulas? Do you remember what they are? Some of you might. They're actually really, really, really similar. For sine, we'd have a 1/2. For cosine, we'd have a 1/2. For sine, we've got a 1. For cosine, we've got a 1. Excuse me. For sine, we have a minus. For cosine, we have a plus. But for either of them, we have a cosine 2x. Now, I'm wondering if you see why this helps us. Chain rule works for derivatives. What are we doing?
Substitution.
Aha. So, can you do this derivative by itself? No. But if you change it, can you distribute that? Easily. Can you do this integral? Yeah. Integral here? Not so much, unless you want to do the reduction formula. You can do that, I suppose. Integral here, piece of cake. Very easy, because that's just a simple little substitution. You'd probably do it in your head, and then you're done with that integral. Show of hands if you feel okay with that one. Good. Would you like to see a couple examples? Yeah, let's bring it on, right? So, let's consider that. Let's go through the whole process, okay? First things first. Does that fit in our integration table?
No.
No. Will you do a substitution?
No.
Maybe. I don't know yet. We don't know. What this is designed to do is make your integral possible, okay? So we're going to manipulate this thing until it's possible. So notice, we're not doing hardly any calculus at all right now. All we're doing is using some identities, breaking this stuff up, and then trying, hopefully, to use a substitution. So, let's see. Is it definitely going to be integration by parts all the time? No, not necessarily. So check it. What do we have here? Do we have a case 1 or a case 2?
Case 1.
Okay, we have some odd powers. If you have an odd power, you're in case 1 no matter what, okay? So case 1. In this case, they're actually both odd. So what we're going to do is we're going to look down here. If both are odd, pick one that will give a power 2. So what I like to think of it, pick the smaller one. That's going to be a little easier to deal with because you can substitute out with the other one. So, okay, we got cosine to the third, we got sine to the fifth. Fortunately for us, they have the same argument. If they didn't, it'd be crazy, all right? So we're going to leave that the way it is. We're going to look up at our powers. What one would be our appropriate, I almost said stripper, our appropriate stripper here. The stripper offer, which one do we want to strip off? The sine or the cosine?
Cosine.
Cosine. I'm not going to edit that, by the way. That's funny. So cosine to the third power? No. What I'm going to make this cosine to the second power of 2x. Watch the way I do this, so hopefully this will make sense to you. I'm going to write the sine to the fifth power. We're going to leave that there. I'm going to put the extra cosine that I stripped off over here. Don't lose track that this is actually cosine of 2x. Don't lose the argument. Okay, it is 2x there. Okay, I want to see if you guys understand that this is exactly the same as this. These two things are the same. Show of hands if you feel okay with that. Good deal. Now, why did we do it? Well, check it out. Now that we have a cosine squared in there, we change it from an odd to an even. Cosine squared, we have an identity for that. So instead of cosine squared, we go, no. Well, cosine squared, it says for odd powers, try to use the Pythagorean identity. Okay, well that's this or the reverse. Cosine squared equals 1 minus sine squared. So cosine squared of 2x, no, this is 1 minus sine. This part is this part. Pythagorean identity says so. Don't forget about the 2x. I can't stress enough how important that is. Some of you people who don't do well in the chain rule, you need to do well here with substitutions. You can keep an eye on it. After that, we have sine to the fifth power of 2x. We've got cosine of 2x dx. Okay, I want to make sure you're still okay with that. Are you all right with it? Have we done any calculus yet? No, it's just trig. Just some trig. Just some identities, actually. Now, here's the awesome thing. As soon as we do this, check it out. This is why we stripped off one of the cosines and left it over here. Watch. Imagine u equaling sine of 2x. What's the derivative of sine of 2x?
Negative.
2 cosine 2x, because you have a chain rule. That's right. Do you see a cosine 2x over here anywhere? Awesome. That's why we do it. So when we get this, check this out. See how this works. You don't have to distribute this right now. Don't be crazy. Leave it just like this. Just like this. And watch. Here's why. If I pick u equals, look, don't pick with substitutions. With substitution, you go through the whole process. Is it in the integration table? Heck no. Can you do a substitution? Yes. Don't go to integration by parts. Don't start doing crazy things if the substitution will work right now. Pick the substitution. Substitutions are typically on the inside of something. Remember talking about that? Inside of something. So it's not going to be to any power. It's just going to be sine of 2x. If the derivative is there, your substitution is going to work. So pick u equals sine 2x. du. We all should be pros at this right now. Derivative of sine of 2x is 2 cosine 2x. Where's the 2 coming from? dx. I know many of you have done substitutions 2 different ways since I've been teaching you 2 different ways as well. I'm going to stick with that. There's 2 ways to do this. You can solve for dx completely and get du over 2 cosine 2x, or you can just divide by 2 and get du over 2 equals cosine 2x dx. Hey, do you see this anywhere in our integration? That's why we put it last. Put it last because it sticks out like a sore thumb. This thing is right here. What that means for us is our integral is going to get really, really pretty right now. Let's see what we've done. Do we still have an integral?
Yes.
Do we still have a 1? Hello, are you with me?
Yes.
Okay. We still have a minus. Instead of sine of 2x squared, what's this whole thing going to be?
Squared.
Already it looks nicer, doesn't it? What else do I need up here?
Your bracket.
Bracket or parentheses, I don't care which, but you have to have them. Now, check this one out. I get sine to the 5th power of 2x. Sometimes, like in your past substitutions, you don't substitute everywhere you see the same thing because you're going to simplify it out. Sometimes you do. Here we're going to. They're going to say, hey, if sine 2x is u, that's also u. This is u to the... Okay, one more. Instead of cosine 2x dx, we're going to have... I need to show of hands if that makes sense to you. Now that's beautiful. Here's why it's so nice. What do you do with the 2?
Put that on front.
Does it become a 2 or a 1/2?
1/2.
Careful on that. So 1/2 integral. What are you going to do here?
Distribute.
This is why we wait to distribute here. We don't do it here. This is crazy, okay? If you had to distribute here, look at this. If you distributed here, you'd have this whole thing, and then you have this thing again, right? That's silly. You do 2 substitutions and it would work, but it's going to make it way harder, all right? We just wait till here, so it's so much nicer. Now we can do our substitute, our distribution. And get u to the 5th minus u to the 7th du. Man, that's like the first type of integral you saw in Calculus 1. That thing is easy. We get a 1/2. Put your bracket there. Don't let yourself make a mistake of not distributing this later. We got, what is this anyway?
Well, u to the 6 over 6
Perfect.
minus u to the 8 over 8.
Are we done?
No.
We're almost done. We're going to do 2 things. What is it?
Plug u back distribute.
It's going to distribute. So we're going to have 1/12 and 1/16. But we're not going to leave it u. What are we going to do?
Sine 2x.
Here's our u. So we're going to have here, all the way down here. You can write it a couple different ways if you want to. Here's one way. You could do sine of 2x to the 6th power over 12 minus sine of 2x to the 8th power over 16 and
Plus 8.
plus c. Of course, you could do, if you don't like the over 12, you could do 1/12, you could do minus 1/16 of 2x plus c. You could factor if you really wanted to, but this is what I'm looking for from you. Show of hands if that actually made sense. Is it that hard? No, but here's the thing. The math here, I promise you, it's not hard. It's just you got to follow the steps, like precisely, and you got to be able to identify what case you're working with. The first step here is the hardest. Not the hardest, it's the most important. So the first step in doing this correctly is really, really key for you to get the correct answer here. If you strip off the wrong thing, it's going to take you either 10 times longer or it's not going to work out for you. All right, so let's get started. So what we're working on, we're going to continue working on some of these trigonometric integrals. And yeah, they get pretty hairy, but we have some cases, some ways to deal with these things that make them at least a little bit nicer. We have a technique, a method to go through this. So let's consider some of these. We'll gradually make them a little bit more difficult so you can see some different ideas that we have to work with. Let's look at the integral of sine cubed x cosine squared x dx. Now, I gave you some cases. What I said was there's really 2 of them. Either you have at least one odd power or you don't. If you have case 1, if you have at least one odd power, the goal is going to be split off either a sine or a cosine of that odd power and then use a Pythagorean identity. If you can use a Pythagorean identity, you change it from sines and cosines to either all sines or all cosines. Does that make sense? That's the idea here. So I want you to get familiar with what you're doing. Don't just follow this like a pattern, really understand what we're trying to do. We're stripping off one of these things, firstly, so that we can make a Pythagorean identity substitution, substitution, and then we'll have all of one type of function, either sines or cosines, with the exception of that one thing we stripped off. The reason why we need that one thing we stripped off is because then a regular u substitution will work really, really nice. So let's look at our problem. Do we have an odd power? Are they both odd?
No.
Okay, so if one's odd, that kind of makes our choice easy as to what we're going to do. If there's one odd, we're going to strip off one of those factors and use the Pythagorean identity. If they were both odd, we typically pick the smaller power because that will usually give us a Pythagorean identity easier. Does that make sense to you? So, for us, what are we going to pick for the thing that we're stripping off here, sine or cosine? And why are we picking that? It's odd, and if I strip off the sine, I'm going to get sine squared. That's the Pythagorean identity I'm looking for. So here, we're going to write this, and I typically write it this way. I'll write my sine squared x first, and then my cosine squared x, and then I'll put my sine x at the very back. Whatever you strip off right there, you put it at the back. And the reason is because what's going to happen, again, the idea here, use this to get a Pythagorean identity. That way sines become cosines. These will all be cosines. And then I can make a substitution. Hey, what's the derivative of cosine?
Yeah.
Oh, sine.
Sine, yeah. So that's the idea. Is we're trying to get to that. We're trying to get back to this going away. So, by the way, some people ask at this point, well, wait a minute, why don't I use the Pythagorean identity on this one right here? Well, if I do, then I'm going to get sine to like the 5th power somewhere, and that's not a good thing either. We want to be able to make that substitution and get rid of this. So, as soon as we get our odd power, we strip off one of the factors, then we go ahead and say, well, the method I gave you said, change one of those things by the Pythagorean identity. Whatever you stripped off, that's what you're left with. So this thing is going to be, what is it? Yeah. The rest of this stuff is still here. The rest of that is right there. Quick head nod if you're okay with it so far.
Yeah.
If you're going, well, now why does that help us? Well, why it helps us is because right now I don't want you to distribute. That'd be silly, okay? Because this whole thing, we'd have to go here and here. You'd have 2 integrals instead of our 1. We want to make this easy. Right here, if I do a substitution on cosine and make this u and make this u, what's the derivative of cosine again?
Sine.
Negative.
Close. What is it?
Negative.
That's going to go away. Yeah, my integral is going to change to a negative, but that thing's going to go away. Does that make sense? This is the idea. If you have an odd power, break off one factor. Use an identity, make a substitution. That's how it works often with this stuff. So here we go. Wow, this is really nice. As soon as we see this, don't worry about distributing or anything, because if we do a basic substitution for cosine, do I want cosine squared or just cosine? What do you think?
Cosine.
Yeah, just cosine. If I have cosine squared, I got to do the chain rule, and that's really annoying because I'll have cosines and sines coming up at us, and we don't want that. So du equals negative sine x dx. When I'm doing my my substitutions on a lot of these trig integrals, I won't solve it for dx. I know I showed you that sometimes I don't. What I typically do is just move this sine or any constants over. So negative du would equal sine x dx. Because, and this is why we put this at the back end. Do you see how this piece matches up perfectly with that piece? You guys see what I'm talking about? That's what we want. So I move this at the back end because this is now a really nice, easy substitution right there. Okay, so why don't you tell me what's going to be on the inside of our integral now? What do
1
we got?
minus u squared.
Okay, good. We got the 1. Minus what now?
U squared.
Cool. Cosine is u, so cosine squared is u squared. Excellent. What else?
Times u times sine x.
Times u times what?
Sine x.
U.
Oh, u. No. We got rid of the sine x.
U squared. Okay, so we got 1, I got minus, I got u squared, I got another u squared.
du.
There's something a lot of you love missing. What are you missing right now?
Negative du.
Oh, besides that.
Parentheses.
Missing parentheses. That's important. Why is that important?
So you know.
For some reason, some of you guys have the tendency to miss parentheses and still distribute because in your head you like know they're there or something. It's really important for you to put those. You need them to say this is what I'm doing. Otherwise, this math kind of falls apart. You need to show that. So these parentheses are not trivial. And then, now, sine x dx is the same thing as what?
Negative du.
Okay, we don't want to forget the negative du. So times negative du. What are we going to do with this thing right now? What do you think?
Hold the negative out.
Hold the negative out. Okay, so negative integral, what else are we going to do?
Distribute.
That will be u squared minus u to the fourth. Don't forget the du. Don't get sloppy with this integration. You got to show all this stuff. None of it is trivial. You guys okay with this so far?
Yeah.
We just changed a really nasty integral. We go, man, how am I going to do that? Something really, really easy. This is brilliant. This is nice. So we'll have negative, what's the integral of u squared?
U thirds over 3.
Minus what?
What is that? U to the 5th over 5.
Would it be positive?
Well, you tell me. What am I having wrong here?
Now you gotta distribute the negative.
Okay, so if I don't have my brackets, then this is wrong. If I do have my brackets, then we have negative u cubed over 3 plus u to the 5th over 5. Naturally, you could write this in the reverse order. Might be a little bit nicer to do u to the 5th over 5 minus u cubed over 3. Now, we don't want to stop there. What's the next thing we got to do?
Plug your u back in there.
That's very good. So whatever our u is, we'll have, and I'm going to reverse this right now. So I'll have cosine to the 5th power of x over 5 minus cosine to the 3rd power of x over 3 and plus c. That's the idea. I'm wondering if that makes sense to you. By show of hands, can you show me if that does? Easy, medium, hard, what do you think?
That was alright.
Kind of medium, right? This part, as soon as you see this is easy. This should be easy at least. This part is the part that people struggle with. Like, how do I do it? You got to get used to seeing these things, following the pattern. You know what I mean? That way you go, okay, hey, look at this odd power. That's an even power. I'm going to strip off one of those things. That's the idea here. Shall we do another one?
Yes.
So far I think I've given you 2 odds and I've given you 1 odd. Let's see how it works with this example. You know what? I'm going to need some more room. Do you have any questions on this? Because I'm going to erase it. Some of these things take a while, so. Okay, so now we're going to do sine to the 4th, cosine to the 4th. So as soon as you see this problem on a test, yes, you're going to have something like this on a test. As soon as you see this on a test, you go, all right, cool. How in the world are we going to do that? Well, go through the pattern. Do we have at least 1 odd power? Okay, so they're both even. If they're both even, the idea of Pythagorean identity goes out of your head. Because if I do this, if I strip off either a sine or a cosine, I'm left with an odd power. Does that make sense?
Yeah.
The Pythagorean identity is not going to work with an odd power. Your substitution won't work because you'll have an extra sine or an extra cosine somewhere. That's not a good idea. So if you have both evens, the idea is you're going to manipulate this thing a lot. It's going to be a lot of work. But what we're going to be using here is the half-angle formulas, where we have sine squared equals 1/2 1 minus cosine 2x,
Yeah.
and cosine squared equals 1/2 1 plus cosine 2. Very good. So we're going to be getting down to those things here in just a minute. So let's work on how we might go about doing this. And there's a few ways to do it, okay? So here's what I do. If I'm working on this problem, the first thing I'm doing is I'm going to try to make this either all sine or all cosine. If I have the same power like 4, 4, we can typically do this. Check this out. Well, I could make sine x, cosine x, all to the 4th. Is that true?
Yeah.
Sure, I could do that. My idea right now is to combine my sines and cosines with some sort of an identity. Right now, if you don't know it, I can actually do that. So if I'm looking at sine x, cosine x, I'm going to use this identity over here. Do you know this one?
Sine x to
2x.
Do you guys know that one?
Isn't that times cosine 2x too? Yeah.
no.
That's the right one. Do you guys know that one?
Yes.
Double angle?
No.
Okay. Well, check it out. We can manipulate identities all the time. If we know they're true, we can manipulate them. So if I take this thing looks a whole lot like this piece, don't it?
Yeah.
Well, I'm going to make this be exactly like this. I'm basically just going to divide by 2. Then sine x cosine x equals 1/2 sine 2x.
Oh, look at that.
We okay with that?
Yeah.
Show of hands if you feel okay with that one. Well, what that means is, hey, look at that. I can make it sine x cosine x to the 4th. Of course, this is a special case, okay, where they're both exactly the same power. If they're not exactly the same power, then naturally this won't work. But I want you to see this at least once, where they're both the same power. You got me?
Yeah.
So we can do this, okay. Then this piece is 1/2 sine 2x. So our integral is integral of 1/2 sine 2x all to the 4th power dx. Y'all still okay?
Yeah.
You sure? Let's keep on moving. What's the next thing that I need to take care of?
You substitute.
The one. Oh, no, wait.
I don't care really about this u substitution, I really don't. Because it'd be very trivial, u equals 2x, you'd have a 1/2, sure, don't worry about that. We can do that basically in our head. What I'm worried about, and we're going to be changing things, so if you do a u substitution on this now, you're going to have to do it later again too. So don't worry about it until the very, very end when you're actually evaluating the integrals. Does that make sense? Don't worry about it right now. What I do want to get rid of is, this looks kind of nasty to me. Can I take this to the 4th power and this to the 4th power?
Yeah, you can.
Okay, let's do that. So I'm going to have the integral of, what is 1/2 to the 4th power?
That's 16.
You know what people do when they're just learning this, or when they're going too fast on a test or their homework, is they'll forget about this guy and they'll give me 1/2 again. Do you see how common that might be? When I'm grading papers, I see that a lot. Where are they getting 1/16 from? I'm getting 1/2 all the time, my goodness. Well, you might not be taking that to the correct power. So be careful with this stuff. This whole thing is being raised to the 4th. Now, if you understand that concept. Okay. Okay, then I've got sine to the 4th power of 2x dx. Looks a little bit nicer. What's the next thing I'm going to do?
Without that constant.
1/16 integral sine to the 4th 2x dx. Now, stop for a second. If you were so inclined, thinking about what I taught you back in the last section, what could you use here?
Reduction formula.
You could use the reduction formula. It would absolutely work right now. Do you guys see why?
Oh, yeah.
Well, there's no why, I know. But there's a sign. Look at the sign. It's to the 4th power. That power is greater than 2, greater than or equal to 2. You could use reduction formula right now. In fact, we did sine to the 4th in class just like 2 days ago. Remember, well, 2 days ago you took your test, but 3 days ago. You remember doing that?
Yeah.
It was the last thing we did. You could do it right now. You could just make a substitution. This is where you do it. U equals 2x. du over 2. This would be 1 over 32. You got me? Then you got sine to the 4th of u du. And you do reduction formula like, I think it's 2 times. You do reduction formula twice. And you'd be done with this thing. Do you guys get what I'm talking about? Look back in your notes or watch the video from the last section if you don't remember how to do reduction formula. Now, what if you don't see reduction formula? Is there another way to do it? And the answer is yeah, which is really interesting because what's going to happen here is we're going to get our integral evaluated and it's going to look different than if we had done this with reduction formula. Reduction formula will work. It will be equivalent, but it's going to look different. Does that make sense? Now, I don't care how you do it. If you see this, I've already taught you reduction formula, right? You can do it. That's fine, anytime. If it's sine to some power, go for it. Some of us have, a few of you have proved the reduction formula for cosine. Go ahead and use it. Your answers are going to look a little bit different than if you do it this next technique. So, technique 1, you work it all down, you go, hey, I see reduction formula, I can do that. It's sine to a power greater than or equal to 2. No big deal. Remember that one, it's the 1 over n, and you know, sines and cosines and a minus and 1 over, n over n minus 1 over n integral, and it reduces it for you. Well, let's say you don't see it. Is there a different way? And the answer is yeah. If there's not a reduction formula possible, or you don't see it, we can still do this with those half-angle formulas. And here's how you'd work it. Instead of thinking of this as sine to the 4th power, what we need to do is we need to find something that will allow us to make this substitution. We need this, basically. So when we get down to here, we go, man, how do I do it? Reduction formula. If you don't see reduction formula, you're going to have to rewrite this again. So how we're going to rewrite it is 1/16 integral. Let me rewrite sine to the fourth power. How am I going to write it as something like sine squared? What do I do?
Sine squared 2x and sine squared 2x.
I'm going to change what you said just a little bit. I want sine squared 2x to some power. What is it?
Squared squared.
You all right on that one?
Yeah.
Now, as soon as you do that, as soon as you go, well, wait a minute, here's some even powers. I know I'm gonna be using half angles somewhere, unless I do reduction formula that works out that nicely, we can do that. But if we can't, then we're gonna have some sort of a half angle formula coming up somewhere, and here's where we go with it. So from here, we still get a 1/16. Sine squared, let's do sine squared 2x, let's make it into the cosine. Here's why we do it. If we take sine squared and we change it to 1/2 1 minus cosine, maybe you don't know why we're going to do this. What's the power here?
2.
What's the power here?
1.
It basically reduces the power for you. Does that make sense?
Yeah.
You can do the integral of cosine to the first power. You can't do the integral of sine to the second power the way it is. You need reduction formula, or you need to make the substitution. So we're going to do that. Use the identity. Now let's be real careful with this. Don't lose your stuff. What's the power going to be up here?
2.
Okay, and then inside, let's do that. What's going to be?
1/2 parentheses 1 minus cosine.
1 minus. Okay, I like that. 1/2, 1 minus, and then cosine for sure. Now, be very careful. Don't lose pieces of this thing.
2x.
It's not 2x. Explain why is it not 2x?
Because it starts from 2x.
What's the argument of our sine function here? And this says whatever your x
Also
is,
is 4x.
whatever your x is, you're going to multiply it by 2. So if we have x, yeah, it's 2x. If we have 2x, it's going to be
4x.
Do you see how common of a mistake that's going to be for some people in here?
Yeah.
Okay, don't make that mistake. Because then when you do your substitution, you'll have a 1/2 when you should be having a 1/4. Does that make sense? Or a 1/8 or something. So this is going to be 4x. Be careful with your math. Show of hands, feel okay with that so far? Good deal, okay. Now what? Goodness gracious. Well, if we're doing it this way,
Substitution.
we can't do a substitution.
Right.
Because if we substitute for cosine, is there a sine anywhere to be had? We can't do it. The only thing we can do here, distribute all this junk. So what I'm going to do, same thing I did here. I took 1/2 to the fourth. We're going to take 1/2 to the second. How much is that going to be?
1/4.
So I've got a 1/16 out front already. This is going to give me a 1/4. Don't forget about that guy. You need that. So 1/4, you know what I need that bracket. Hope you follow the notation here. All we did was we took 1/2 squared, it's 1/4. We took this thing, now this thing, I think I missed one there. Now it's this thing squared, 1 minus cosine 4x to the second power. Quick head nod if you're okay with that one. Can you guys distribute this? Are you just going to square this and square this? Please, for heaven's sakes, don't do that. Remember that what this means is 1 minus cosine 4x times 1 minus cosine 4x. Would you please spend some time and distribute that for me? Go ahead, distribute that for me. What I'm going to do is I'm going to pull the 1/4 out front. We have a 1/16. We now have another 1/4. What's 1/16 and 1/4? How much are we going to get there?
164.
164. Then, so this now combines for 1/64. You guys are distributing this right now for me, so hopefully you get this. It's usually not very hard. You guys know how to FOIL. This is 1 minus 2 cosine 4x plus cosine squared 4x. How many people got that? Perfect. That's what goes here. Let's take a real close look at our integral and see what we got going on. If I asked you to, could you do the integral of 1?
Yes.
Yeah, no substitution, that's a piece of cake. Could you do the integral of cosine 4x?
Yeah.
Yeah, what's the integral of cosine? Now, you'd have a 4x, so that'd be over 4. You'd need a little substitution. I typically do those in my head. U sub on that would be over 4. Does that make sense to you? Now, can you do this one? Okay, let's try this again. Integral of this, could you do it?
Yeah.
Easy. Integral of this, could you do it without a substitution? With a little substitution, but that's easy. Can you do the integral of cosine squared? Is that anywhere in your integration table?
No.
We got to go over again. So we start from the very beginning with our trig stuff. What power do we have? Odd or even? Even power. With even powers, we use what? Pythagorean identity or half angle. Which one? Do we know a half angle for cosine squared?
Yeah, we do.
Then that lets you break that down again. There's lots of steps here, lots to this. Be very careful, write these all out. I know some of you don't like to write steps, and I'm going to say, too stinking bad, do it anyway. You got to write this. You got to be able to do this. And make no mistakes on it. So we have 1. We got minus cosine 4x. We've got a plus. Let's look inside here. Remember that cosine squared x equals 1/2 1 minus cosine, plus cosine 2x. Hopefully we're familiar with that one. Let's apply it here. I've got the 1, I've got the minus cosine 4x, I've got the plus. What am I going to write next? 1/2. Got it. Keep on going. Come on, tell me.
1 plus cosine 2x, but don't forget the parentheses.
Oh, 8.
Okay, now,
8.
you all need to be careful on what the argument of that thing is going to become. Listen, we're starting with cosine squared of 4x. If cosine squared x gives me cosine 2x, cosine squared 4x gives me cosine... Remember, you're taking your argument, you multiply it by 2. What is it?
8.
Perfect. Okay, I'll tell you what, we're almost done. I want to do about a 10-second recap to make sure you guys are good with this stuff. You okay with the making it all do the 4th power?
Yeah.
It's a special case, and I get that. You're not always going to have the same power there. But when you do, man, try something like this. It's kind of nice. Use an identity. Are you going to have to know your trig identities? Yeah, otherwise this stuff doesn't make sense. You got to have that down. People take calculus 2 to finally fail trigonometry. People take calculus 1 to finally fail algebra, all right? But this is trig. I mean, my goodness, we're going to use a lot of trig. Then we go, okay, well, that's cool. You know what? We can just take it all to the 4th power. We recognize this one as either a reduction formula that we could do, which probably would be a little bit quicker than this, to be honest with you. Sometimes you won't be able to do reduction formulas, sometimes you will. Or we go, well, I didn't remember that, so let's practice doing the whole even power thing. The even power thing is make it a sine squared or make it a cosine squared somehow. Then use a half angle. Cool. Then distribute it. Look for any more squares. You're basically reducing this with the half angle formula. It's like an inherent reduction formula. The half angle formula always reduces your power. Do you get what I'm saying? So we look again, we go, okay, well, we got to do it one more time. Half angle again, reduces the power one more time. Now we have everything to the 1st power. We got 1, no big deal. Cosine of the 1st, we're going to distribute this in just a bit. Cosine of the 1st. Let's pretty this thing up a little bit. What are you going to do here? Let's do it. We want to make our integral as nice as possible before we actually integrate. So we got 1/64. We're going to have 1 minus 2 cosine 4x. Don't lose track of that 4x. Plus 1/2 plus 1/2 cosine 8x dx. Okay, I'll tell you what. Whenever you distribute in algebra, the one thing that you should probably do after you distribute is check for what? That's right, like terms. Do we have any like terms here?
Yeah.
Yeah, just combine those numbers. This is 1 and 1/2, that's 3 halves. That'll make you integrate one less term here, which is kind of nice. Combine your terms if you have any. Can I combine cosine of 4x and cosine of 8x?
No.
That's a no-no. So 1/64, we got 3 halves minus 2 cosine 4x plus 1/2 cosine 8x dx. My goodness, that's a lot of junk. I want to make sure that we're all good to go. Do you guys feel okay on what we've done so far? Yes, no?
Yep.
Okay. Can we integrate that little piece?
Yes.
This one? This one? It's the same thing. It's integrated. when you do it, just be real careful with your constants. That's typically, I mean, almost nobody gets the integral of cosine wrong. Y'all know it's sine. It's the constants that are going to get you here. So don't lose track of stuff. We're going to have 1/64. We're going to have a big old bracket here. Let's integrate piece by piece. Integral of 3 halves. 3 halves x. Very good. Minus, here's how integrals work. If you want to do these in your head, this is the way I do it. I do little substitutions in my head because I don't want to waste my time. So watch. Watch. Here's what you do. The 2 is a constant, correct?
Yeah.
Integral of cosine?
It's sine.
It's sine 4x. What's the derivative of 4x?
4.
Over 4. That's how you do it. So derivative of this thing, that's a basic substitution when you just have constants. It'll typically work with those arguments. You should put it over whatever the derivative is. If you notice, this is coming from the du over 4 that you would get. Does that make sense? So that's where that's coming from. Let's try the next one. What's the next thing I write?
1/2
Next thing.
sine 8x
Sine 8x.
over 8.
Perfect, over 8. Now we're able to do those without actually having to write a special substitution on that, because that takes a little while, right? You have a substitution here, you have another substitution here, that takes some time.
Can that 2 and 4 cancel out?
Well, we're going to talk about that right now. I want to make sure you guys are good on this so far. Show of hands if you are. Okay, so yeah, a few things are going to happen. Of course, we're always going to look at simplifying. 2 with 4, done. This becomes what?
16.
Okay, and then maybe we'll distribute. Maybe you won't. It kind of depends. I'm going to distribute because I want to. So we'll have 3 over 128x. Oh goodness. We'll have minus, when we distribute, notice this is a 1/2.
Yeah.
1 over 128 sine of 4x plus, wow, what's this going to be? So basically you have 64 times 2 times 8, or 64 times 16. I don't even know. You tell me what.
1024.
Sounds good. I'll take your word for it. Sine 8x. And finally,
Plus C.
plus c. Wow. Wow, that was a lot of work. Could you have left the 64? Absolutely. No problem. You could have just left it. Factor. You could factor out something else. Your question.
Totally should have just factored out a 1/2.
Yeah, you could have. Could have factored out 1/2 and made it 128 and then 3x. Should have just done reduction formula. That's right. But you know what? There's times when you can't, right? So I want to get you really practicing this. The next one you see that we're going to be able to do that as well. But I want to see you practicing this method. Does that make sense to you?
Yeah.
So I get it. The reduction formula works. That's what I would do. Notice that this is going to be a little more concise than the reduction formula. Reduction has sines and cosines in it. So this would be a little bit nicer in my opinion, but you could do it with reduction formula. Are you guys ready for the next one?
Yeah.
Okay, the next one's going to be some work. Question?
If we were to use the reduction formula, is it possible that we could get something that looked different but was equivalent to that?
That's actually just what I was saying, is that when you do reduction formula, it's going to have sines and cosines. The integral will be equivalent, and you can get the same thing with identities, but it's going to look different. Okay?
Well, how can you know it's the same thing?
You do the identities to prove it. Like all those times in trig where it said, prove this identity. That's how you do it. That's why they had you do those. That's why they had you do those. So anyway, let's continue. Let's do this one.
Integral of sine, easy peasy.
Hey, there's no dx there, so I drew this one wrong. You just say, can't do it. Oh yeah, did you have any questions on that? We're good. Okay.
Just watch the video.
That's right. Watch the video again. Hey, there you go. Questions? Too bad. Just joking. Let's make this sine to the 6th dx. Now, what would you use here? I would use reduction formula. What if you didn't know the reduction formula, forgot it, just missed it, or just want to practice like I do on doing it differently? Can we do it?
Yeah.
Of course we can. Is it going to take a lot of work?
Yeah.
Yes.
Yes, it is. So, How would you do it if you didn't have the reduction formula?
Sine x to the 6th power.
Sine of x to the you're close, but no. You see, if I have even, let's look at the powers. Look at them. Do I have odd powers?
No.
I actually have 2 even powers. If you don't think there's 2 of them, kind
Two
of.
odd.
Cosine is 0, so it doesn't really count, but I have sine to the 6th power. That's my only power. It happens to be even. So, what are you going to use, ladies and gentlemen, when you have all even powers? Will you use Pythagorean theorem or half angle? Half angles. So we need to make this a half angle.
So sine
Half angle only works if you have sine squared or cosine squared. So somehow I want you to rewrite that with a sine squared. Go for it. And don't write out sine squared times sine squared times sine squared, okay?
That's all.
You could, I guess, but it's going to be the same. But it just looks sloppy. How am I going to write out sine to the 6th power as sine squared to something? Did y'all do that one?
Yeah.
Okay, I want to see if you understand the reason why we just did that. What are we trying to use when we have even powers? Even powers only work when you have sine to the second, or cosine to the second, but we don't have any cosines. So that's the only thing that's going to work for us is to do sine to the second and then do the 3rd power. Are you guys with me?
Yeah.
Do the next step. Can you use the half angle formula here?
Yeah.
Do it.
We're gonna go. Cosine 2x.
Let's see if y'all got it. Did you get 1/2 times 1 minus cosine 2x and then all of that raised to the 3rd power with the bracket?
Yeah.
Cool. Next thing you're going to do, let's do it. What are you going to do?
Distribute that exponent.
Yeah, you are. This is going to become how much?
1/8.
1/8 is going to be pulled in front of my integral. You follow?
Yeah.
Now, what do you have to do with this thing?
Just keep it that way.
Foil it
Oh, you know what, I
times
forgot
3.
something, sorry.
You're going to have to distribute that.
Oh,
So
yeah.
if that was to the, oh my gosh, if that was to a higher power, you'd have to distribute even more. So yeah, you have to, if you're going to do this method without reduction formula, you actually have to distribute that. So on your own right now, off to the side, do 1 minus cosine 2x times 1 minus cosine 2x times 1 minus cosine 2. You're going to have to distribute that. I'll let you do that for about 10 minutes. I'm right on the board here. You're welcome. I think that's right. You want to check? There are easier ways to do binomial expansion. That's one of them. If you know the Pascal's triangle 1, 3, 3, 1, and you know alternating signs with a minus, minus, plus, minus, and you know powers reduce powers gain 0, 1, 2, 3. You can distribute things like that very quickly.
Whoa.
Very quickly. So if I did like to the 4th power, basically it'd be the same. It'd be 1, 4, 1, 4, 6, 4, 1. And then you could, if you know the binomial expansion, you can do that. So anyway, this is what you should have if you distributed it and combined like terms. Did you all get that?
Yeah.
Are you just going to trust me that that's right?
Yeah.
Probably. Okay, that's right. Let's continue. Now look, after you distribute, after you do that, you really do got to look at your problem. See what's going on here, folks. Check this out. Can you do the integral of this?
Yeah.
Then you're going to leave that. Don't bother changing that. That's a good thing. Remember, you could separate this into 1, 2, 3, 4 more integrals. We're not going to. We're going to do it in our head. But you could. So leave this alone. Leave this alone. Can you take the integral of cosine?
Yeah.
Leave that alone. Can you take the integral of cosine squared?
No.
So this is something we got to work on. Okay, let's see if you're paying attention. With cosine squared, would I use Pythagorean identity or half angle?
Half angle.
Why?
Because it's cosine to the square.
Bam! That's exactly right. So this is going to be a half angle right here. Now stop. We're going to do one more thing. Cosine to the third, can you do the integral of this right now?
No.
Change that one too, so this is another one. That's an ugly little star, isn't it? Another little star. If you got cosine to the third, okay, let's think about this. Are you going to do half angle? Or are you going to do Pythagorean identity? Why?
Because it's an odd.
Odd. That's right. That's exactly right. So let's go slow. I want you to just do the half angle right now on this guy. Just do that. Let's see, 3, that I know this thing is 1 plus cos, well, let's see if you got it. This part right here is 1/2, 1 plus cosine.
4x.
Brilliant, 4x. Did you all get the 4x? Good. Minus, let's talk about this one now. If I've got cosine cubed of 2x, you're right, that stands for, that's an odd power. So what do we do with odd powers? Pull one off. Very good. We strip off we get the stripper. We get the stripper on this side. That's right. So we strip one off here, cosine 2x dx. Oh, look at that. We're going to do a couple things at once, okay? So don't get lost on me here. I'm going to leave all this stuff the same. I'm going to distribute this, because that's nice. We want to distribute that. I'm also going to start changing this guy. Show of hands if you feel okay with this so far. All right, so we've got a 1/8. We've got an integral. We've got a 1. We've got a minus 3 cosine 2x. We've got to check this out. This is 3/2 times 1 is 3/2. 3/2 times cosine 4x is 3/2 cosine 4x. So this is exactly the same. All I'm doing is distributing 3/2. So we got those two pieces. Quick head nod if you're right with that one. Now, when you're working with this stuff inside of an integral, you can do two things.
What does it happen?
You can do this if you want to. You can go, wait a minute, this is too confusing for me right now. I don't want to deal with this here. You can write a dx and split off another integral. Does that make sense?
Yeah.
Do it off to the side. Just don't forget it's a minus. You're going to have a bracket around all the junk that you do right now. Does that make sense to you?
Yeah.
You can do it in here too and do the substitutions and or distribute and make things a little bit nice for you. That's what I'm going to do. So either you're doing this off to the side, no problem, or you're doing it the way I'm going to show you. You guys okay with this so far?
Yes.
Okay, so this is like its own little problem right here. Here's how I would choose to do it. I say, okay, well, you know what? This right here, this is the same. What are we doing here? Are we doing half angle or Pythagorean? Because it's connected with this, you do half angle. So again, you would have this integral. So Pythagorean off to the side if you chose to do it. This would become 1 minus sine squared. You want Pythagorean, not half angle. That is cosine 2x. That's supposed to be a little 2 there. And then you do a simple substitution, and you're practically done with that. You guys okay with that one? Okay, maybe I'll do both, just so you see that it works out the same. Over here, what would your u become?
Cosine 2x.
Cosine or sine? Sine. It's usually inside of something. Sine of what? Du, those people who hate to do the chain rule, don't mess this up. What's this going to become? Or du over 2 equals cosine 2x dx. Exactly what we have here. Therefore we get, I know I'm working quickly, but we've already done something very similar to this. This is 1 minus u squared. This guy is du over 2. Or in other words, this is 1/2 integral of 1 minus u squared du. 1/2 u minus u cubed over 3. 1/2 u minus 1/6 u cubed. And lastly, we do our substitution back in. We'd have 1/2, what was our substitution anyway? Minus 1/6 sine cubed 2x. Okay, I know I did it fast, but I want to know how many people could do this on their own at this point. It should be pretty much all of you, because we all know how to do a substitution. This was the only big thing, is seeing. Just really, have you noticed how the hard part about this is seeing what to do? It's not actually doing it. It's going, oh wait, I got a cosine cubed. Is that half angle or is that Pythagorean? It's odd, so it's Pythagorean. This was even, therefore it's half angle. So, well, separate it so that you can do Pythagorean. So cube, no. Strip it off. We've got Pythagorean, we got that. Pythagorean identity, do a little substitution. It works out pretty nicely. Show of hands if you got the same thing on your own. You're okay with that one. Cool. Now, notice something. This integral is done. So this is what you plug back in right here when you're done with the integral. Does that make sense?
Yeah.
It'd be minus this whole mess of crap. Now, if you do it the other way, I don't even know if I want to show you the other way now that we've already done it. It's going to take some time. If you do it the other way, basically just put a bracket here. You do the same thing, sine squared 2x, cosine 2x, dx. You would distribute it. So you would have a cosine 2x here. I would probably combine that cosine 2x somewhere over here. And then you'd have the same substitution that you just did. Does that make sense to you? So you do one or the other way. I'm going to leave that. So I like that way. I like doing it off to the side. So this is going to be minus this stuff. 1/2 sine 2x minus 1/6 sine cubed 2x. I'll put the plus c on the very end of my problem. I don't need to deal with it right now. Okay, so I don't want to lose you. I don't want to lose anybody. So let's check it out. You guys are okay down to here, correct? This one, we said, no. Let's separate this. Let's call this one big fat integral. That's why we got the dx right here where there wasn't one before. Then we're subtracting the integral of this guy. So we said, now let's make this a dx and we'll have the integral of this. So we move that over here. We do it off to the side. It's a problem within a problem. So 1 minus sine squared 2x times cosine 2x. Do the integral, then put it right back. We get the same thing. So are we going to integrate this right now? Heck no. Are we going to integrate this stuff right now?
Yes.
Of course we are. What might you want to do before you start integrating that?
Combine like terms.
Yeah, that's right. And in fact, if you would have done this the other way that I was about to show you, you would have some more like terms to combine. So you'd have less terms. It's whether you want to combine them now or combine them later. We're going to do it at some point. What like terms do we have?
3/2.
1 3 halves.
How much is it? 5 halves. So this is going to be 5 halves. So 1/8 integral 5 halves minus 3 cosine 2x. This is gone. Plus 3 halves cosine 4x. Notice dx. Calculus ends here. This we've already done.
Distribute.
Yeah, you could do that. You could distribute that right now if you wanted to. You want to do that?
Yeah.
So minus 1/2 sine 2x. Good. Plus 1/6 sine to the 3rd power 2x. Now let's work on the integral of this thing. Almost done.
You're forgetting the dx on both of those,
What dx?
the whole integral
It's right there.
for the other one.
The
on
last
top.
is already,
There's a hit.
it's already integrated.
Oh, you split it?
That was kind of the whole idea. Was right here we split this and we did this integral separately. That way we could use substitution and go, yeah, you know what? Let's do this separate. We have it back in terms of x. Now we can put it back. So this was all one integral. This one I said, no, this is too hard for me to do right here. Or you actually could, not a big deal. Or you could do it separately. I just want to give you that option. So either way, and I don't care how. Pull that off. Make sure you get all the way done. Then you plug it back here. But notice, we've already done the integral. There is no more integration to do here. I really do need you to understand that. Show of hands if you do, you feel okay with that. Question? Someone looked like they had one. Question? You sure? Okay. Okay, almost done. So 1/8 times some nasty stuff. Let's do this integral. Can you do the integral of 5/2?
Yeah.
What is it?
5 x.
Minus, be very careful with these guys. This is going to be minus 3. Integral of cosine 2x, please?
Sine of 2x times 2.
No, it's not times 2.
Divide by 2.
When you're doing integrals, you're dividing by this derivative because you're setting this equal to u, derivative of this equals du, so dx would equal du over the 2.
Ah.
Plus 3/2. Let's try this again, okay? Derivative of this one?
Sine 4x.
Perfect. Again, you're kind of doing those substitutions in your head. Minus all this stuff. Oh dear. It's fun, right?
A little bit.
What now?
Distribute to 1/8. And combine that.
So working from the very bottom, 5/16 x. Oh goodness, minus 3/16
Sine.
sine 2x. I know, right? Plus 3 sine 4x.
Wouldn't you have to, yeah.
Minus 1/2 sine 2x plus 1/6 sine cube 2x. Oh goodness, all right, well, almost done. What's the last thing that we're going to do?
Wouldn't you have to distribute the 1/8 on both sides?
We did. We're going to be 8 times 8,
So-
16.
No, it also goes here. Yeah, you're right. This thing's a big bracket.
Oh,
Yeah, you're right. You're absolutely right. So if I distribute that, what's this change to?
So 16
Yeah?
and 40.
How much?
40.
There's only one more thing we got to do. We're looking for any like terms. So like terms, do you see any?
The sine, oh no, the sine 2x, yeah.
This one, no. This one, yes. These two are like terms, and thankfully, because Patrick caught this, we distributed that, and they have a common denominator right now, which is really nice. So we're going to have, I was just testing you, Patrick, you passed. 5/16. How much is that going to be?
4/16, so it should be 1/4.
And lastly,
Let's see.
okay, I want to show you one more thing with this. If you didn't do the integral, so I do want to prove to you that it does come out the same. So imagine you didn't do this right here. What you'd have is 1 minus sine squared 2x times cosine 2x, all dx. You'd have a minus cosine 2x plus sine squared 2x cosine 2x dx. You would distribute this thing, this is what you would combine with this thing. It would be minus 4. So when you look at that, this would become minus 4 cosine 2x. If you do the integral of the minus 4 cosine 2x, you'd get minus 4 sine 2x over 2, correct? That would be the 2. You get 2 sine 2x. When you multiply by 1/8, you get the 1/4 right there. Does that make sense to you? It matches, the coefficients are going to match. So this one would get combined with this one right now. This one is what you do over here. You do the u sub on sine. You get du equals 2 cosine 2x dx. You get du over 2 equals cosine 2x dx. This is what would match right here. If you do a little substitution kind of off to the side. And what you'd end up getting is you'd get u squared over 2. Does that make sense? U squared over 2. So when you do u squared over 2, check that out. U squared over 2 would give you u to the third over 3 times 2. That's 6. 6 times the 1/6. 1/6 times 8 gives you the 148. Here's the u to the third power of the sine 2x. Oh my gosh, that's a lot of work. Either way it works. I just want to prove to you that it actually does. Show of hands if that one made sense. Okay, that's hard, right? What would be way easier?
Not that.
Reduction formula would be easier, but if you don't have it or you can't use it, then this is what you have to do. So, what you should know at this point, odd powers. Odd powers, you use which identity, please? Everybody. Pythagorean. Odd powers, Pythagorean. Even powers. Very good. All right, let's do our last example about integrals that involve sine and cosine. After this, we'll talk about some other types of trigonometric functions like tangent and secant, cotangent, cosecant, that stuff. I'll give you the rules on that after this example. But I want to go through one more, maybe when you don't have some whole number exponents, so you get a feel about what's going on. Now, when we talked about our rules on integrating sine and cosine, there was 2 cases. There was the case where both powers are odd, where both powers are even, or where they have one even and one odd. When you have a fraction like this, look for the other one. This would be pretty hard to deal with, so we're going to look at sine to the third power. What case does this fall under? Does this fall under both even, both odd, or one of them being odd?
One being odd.
That falls under one being odd. Now, when we have that one being odd, do you remember what we do with that?
Break one off.
Break one off. That's right. We strip one off. Remember? We strip it off because what we're going to do is, I hope you know, we're either going to do half angle or we're going to do Pythagorean. What's the case here? It's going to be Pythagorean because we're going to strip one off and change the sine squared. As soon as you change a sine squared to a cosine, the reason why we strip off that sine is because now a substitution will actually work. The derivative of cosine is basically sine with a negative. The derivative of cosine gives you the sine, it's gone, it's out of there, and we're able to integrate the rest with a simple substitution. You ready? So let's try it. So first thing to look at, do we have odds or evens? That counts as an odd, so whenever you get an odd power of sine or an odd power of cosine, strip off the one that gives you a square power. So I don't want sine to the third, I'm going to write this as, what?
Sine squared.
Sine squared x, I like it, and cosine 1/2. I like to write that one first because I like to strip off the sine and put it here because it makes our substitution look a little bit better. Okay, so again, here was the idea. We got an odd power, strip one off, and then what are we going to do with the sine squared?
Turn it into identities.
What identity is that? Is that the half angle or the Pythagorean?
Pythagorean.
Use that one. So here we go. Okay, cool. I like this. We're going to do 0 to pi over 2. We're not going to touch this till the very end. The idea again behind doing this is manipulate your integral so that you can use a substitution. The way that we do that is we try to make these be the same trigonometric function. You have to make them the same. And you have to make them the same so that when you take a derivative, it's this guy over here. So use Pythagorean to change sine into a cosine. Then we'll have all the same stuff. 1 minus cosine squared x times cosine to the 1/2 x times sine x dx. So when we have an odd, strip one off. Now we use Pythagorean identity to make everything besides this guy into cosine. Once we do that, do you see a substitution that's going to work? Yeah, don't worry about distributing. You don't have to do that. Don't worry about that. Just make your substitution. What's your substitution going to be? then du equal, oh, derivative of cosine x, what is it? Negative sine, very good. So we know that negative du equals sine x dx. That is what we have here. So let's keep on going. Can you all tell me what's going to be in my integral once I make that substitution? So we stripped it off. We got all cosines. We're making our substitution. What's this change to?
1 minus u squared.
1 minus what?
U squared.
Perfect. Keep going.
Parentheses.
What next?
U to the 1/2.
Oh, good. So we still have u, cosines u to the second, u to the 1/2.
Times negative du.
Yeah, don't forget that negative. The sine dx is negative du. Okay, tell me what we do next.
Move the negative out front.
Okay, love that. So, moving up here, negative integral of, we'll move the negative out front. We'll keep our bounds of integration. Yeah, let's distribute the u. So right now, once you make the substitution, it's a lot easier to make the substitution then distribute, rather than distribute and then make the substitution. There's less to have to deal with. So when we do our distribution, we get u to the 1/2
Minus
one.
u.
minus, oh,
U to the 3/2.
when we multiply powers together, do we add them or multiply them? You add them. So, u to the first, u to the,
3/2.
Two.
Wait,
Power.
5/2.
let's get that one right. 2 over, let's see, 4 over 2 plus 1 over 2, that's 5 over 2, you get 5/2. I hate to say it, but use a calculator if you have to, I don't care. Get it right, okay? Don't multiply those and give me 1. Oh my goodness. Add the powers. You get 2 plus 1/2, well, that's 2.5, 5/2. That's what that is. You guys okay with that one? Finish that off, go ahead.
You should get 3
You would if you added 1 plus 1/2, that'd be 1.5, that's 3/2. But if you add 2
Oh, it's u
plus 1/2,
squared.
you get 2.5, 5/2. Did you get 3/2 over, u to 3/2 over 3/2? Did you get u to 7/2 over 7/2? What am I missing? Missing a, do I need a plus c here?
Oh, no, we're doing it.
No, because it's definite. Okay, so good. What am I missing?
Negative.
Front of the whole thing.
In front of the whole, do you guys have brackets?
Yeah.
You should, because we're subtracting this whole integral. Okay, so we're subtracting this thing. What's going to happen here? Let's simplify this. What's it look like?
Negative.
Okay, so negative. Negative what?
U to
2/3 u to the 3/2. Okay, I like it. Then what?
plus
2/7. U to the 7/2.
Beautiful.
Would you want to change your bounds on this one?
That's a good question. That depends on you. If you want to change the bounds, then you should have already done it, correct?
Yeah.
If you don't, let's say this. Some of you guys made a little bit of a mistake on that last test. Let's say you don't change the bounds. Do you plug in 0 and pi over 2 here? No. What do you put here?
The x's back?
You'd have to put,
Whatever u is.
this would have to be, whatever u is. You have to put cosine back in there. Then you plug in 0 to pi over 2. Does that make sense to you?
Yeah.
If you go ahead, I like changing bounds personally. I think it's easier, or at least it's more straightforward. So right here, what I would do is I'd say, okay, we start with x's. So if x equals pi over 2, then u equals, and if x equals 0, then u equals, and we just plug that into cosine. So if we do that, we've got cosine of, what's cosine of pi over 2?
0.
And if we plug in pi, let's see, if we plug in 0, what's cosine of 0?
1.
Okay, the only problem that we're going to have here, if you do it this way, please be careful. This is probably good for you guys to see. This is why we're doing it right now. Where's the 0 go? Bottom or top?
The top.
Goes on the top, because pi over 2 got mapped to 0. Does that make sense to you? Okay. Where's the 1 go?
On the bottom.
0 got mapped to 1. Show of hands if you feel okay with that one. Okay, if you do it this way, what happens right here? So other way, if you had this, you'd have to do cosine for your u and then plug in the actual values. That's fine. You go ahead and, if you, someone who had that on the paper, go ahead and do it. Make sure you get the same thing we did. If you do it this way, if you actually change bounds, you should have remembered from your calculus 1 that when you flip your integral, your sign changes. Do you remember that property?
Yeah.
Yeah.
If you flip this and go, okay, let's make it from 0 to 1. Let's put it in the correct order. Negative becomes positive. It changes that. Should you feel okay with that? Okay, and now it becomes, well, something we can do, and we don't have to re-substitute in that cosine. So this would be 2/3 u to the 3/2 minus 2/7 u to the 7/2. We already did that. Now, let's practice this one. If I do this, if I change my bounds, do I have to put cosine x back in for my u?
No.
No, I changed them. These are now in terms of u from 0 to 1. Those are u's now. They were x's. Now they're u's. We just showed that. We get to plug in 1. We get to plug in 0. We don't have to plug them into cosine because we already did over here. That's how we changed it. So we'd get 2/3 1 to the 3/2 minus 2/7 1 to the 7/2. I always plug these in case something funky happens. We get 0, okay, that's going to be 0 minus 0, so nothing's going to happen over here. 1 to any power is still 1, so 2/3 minus 2/7. How much is 2/3 minus 2/7? 824, okay. 8/21. Michael?
It's gotta be negative because the bounds 0 to 1, or 1 to 0 rather, instead of 0 to 1.
We had 1 to 0 with a negative, so when we flip that, the negative changes to a positive. So we are changing, you caught it, we are changing signs though. This would be negative, correct? But if I have a negative out front already, it becomes positive. That's the idea. I want to show of hands if that made sense to you. If you did the other way, you wouldn't do this. You'd still have 0 to pi over 2, but you'd be plugging it into cosine here and cosine there. I want to make very, very sure that you're clear on that one. Are you guys clear on that?
Yeah, it would be
Okay,
plus, right?
awesome. Say what?
You'd have to distribute the negative. It would be positive.
Yeah, you would. If you didn't, if you left it with the original bounds, you would get negative 0 to pi over 2, like that with all this junk. And then you'd have negative 2/3 u, but the u would become cosine x to the 3/2, plus, because you would distribute the negative, 7/2 cosine x to the 7/2. Sorry, I had this backwards, 2/7. And then you plug in not 0 to 1, you plug in 0 to pi over 2. Well, if you look at that, it's going to be the same. Cosine of pi over 2, this is 0. Cosine of pi over 2, this is 0. But the zeros aren't 0. Cosine of 0 is 1. Cosine of 0 is, so this is negative 2/3 plus 2/7. Oh, look at that. It's exactly the same. Just negative. Oh, I missed something, huh? Because we were supposed to subtract them. So it'd be, shoot. Negative 0 plus 0 minus negative 2/3 plus 2/7 is how it would really look. That's the same thing. This, if you distribute, it's 0, 2/3 minus 2/7. That's the same. Same idea. Exactly the same. Make sense now? Even more sense? I know it made sense before, but now it's like extra sense. Anyway, we're going to talk about one more thing in this section. How to do some integrals that maybe don't have just sines and cosines. We've been practicing with sines and cosines all day long, all lesson long. Let's look at something else. Oh, by the way, did you have any questions?
No, sir.
Okay, all right.
Good.
Too late. So, what happens if you have something like, not sine, cosine, but tangent, and probably something else like secant? We group sine and cosine together because the derivative of one gives you the other one. Does that make sense?
Yeah.
And we group tangent and secant together because derivative of one kind of gives you the other one, especially with like secant squared and things. And cotangent and cosecant. So those ones are grouped together because it's possible to do. If you don't have that scenario, you have to change things to sine and cosine and work it a different way. I'll give you that example much later. So like at least another day. So what about integrals that involve tangent and secant? Or cotangent and cosecant? I'm hoping that you understand the ideas that we use here. We're going to use the same exact ideas here because the tangent and the cotangent, the secant and the cosecant, they work really similar and the identities are very similar. So let's take a look at what we do with this one and we'll use a corollary for this one. So here's the deal. Just like we have rules for sine and cosine, we're going to have rules for tangent and secant. If tangent is odd, so if tangent's an odd power, if the power of tangent is odd, what we're going to do is something kind of fancy. We're going to strip off not only a tangent, but we're also going to strip off a secant. So we're going to keep a tangent and a secant. I'll explain why in a second. So if the power of tangent is odd, keep one factor of tangent x, secant x. In fact, I'm going to write it backwards. So we're going to keep a tangent, we're going to strip off both a tangent and a secant. Keep one factor of secant x, tangent x. I'm going to write it this way because it's going to make a little bit more sense right now. Remember the idea behind this? I hope that you do. The idea is that we're going to break off a little piece, right?
Yeah.
We're going to break off a little piece so that we can take the derivative. So if tangent is odd, if tangent's odd, like 3, we're going to strip off a tangent. That's going to make the remaining power a 2. Tangent to the second power has an identity. It's going to change into secant. Hey, what's the derivative of secant?
Secant tangent.
That's why we're keeping that, because this will allow us to do a substitution. So if the power of tangent is odd, keep one factor of secant tangent and use tangent squared x equals secant squared x minus 1. What that does, that changes all but this tangent into secant. Then you can use a substitution. The derivative of secant is secant tangent, and you're pretty much good to go. Now, let's say that the power of, so we check first the power of tangent, okay? If it's odd, you're good. Then if it's not, we're going to check secant. Let's say the power of secant is even. If our secant is even, what we're going to do is we're going to keep or strip off a secant squared and use secant squared x equals, let's see, what would that be? Tangent squared x plus 1. If this is the case, if we have an even power of secant, well, then what we can do is strip off the even, the rest of the even, and keep a secant squared. If we keep a secant squared and use this to translate everything else into tangent, hey, tell me something. What's the derivative of tangent? Secant squared. That's going to allow us to make a substitution. Tell you what, I want to try at least one of these right now, just to get it in our heads real quick so the stuff makes sense, okay? So, You'll find a lot of similar patterns to sine and cosine. Same idea. It should be a little bit easier now that we have this stuff down. Question?
Oh, so those two definitions, those work for either, both of those, cotangent or cosecant too, like?
That's right. So if, and I'm kind of putting this up here for this one too. You could read it this way. If the power of cotangent is odd, keep one factor of cosecant cotangent and use cotangent squared equals cosecant minus 1. You'd use that one. Does that make sense to you? If the power of cosecant is even, strip off cosecant squared and use the appropriate identity. You guys with me?
Yeah.
Okay, so make sure your identities are good to go and we'll be absolutely fine. Very similar ideas here, which is why I'm not going over this one completely separate. They're the same, it's the same thing. Let's try one, I'll give you one in a while too, but let's try one with tangent and secant first. All right, let's go through the whole process here. We're going to look at the power of tangent first, and if it fits our paradigm, we're good to go. If it doesn't, well then we got to look at the power of secant. So let's look at the power of tangent. What do you notice about it?
It's
It's odd, and that's great. That fits right here. So what we do with the odd power of tangent, we're going to make it even. We're going to strip off a power of tangent, but we're also going to strip off a power of secant. So what am I going to write as far as the tangent goes? Tangent
to the fourth.
Yep. Tangent to the fourth. And I'm also going to do secant to the...
Second.
Now here's what we're going to do with that. We just stripped off the tangent. We just stripped off a secant. I'm going to have secant x, tangent x, dx. I want to make sure that you guys are all right with this so far. Raise your hand if you are okay with that. It's just some algebra. It's just understanding that this is the same thing. I'm just doing this on purpose because right now I'm working to make a substitution. That's the idea. Now, do I want to change secant squared?
No.
No. Some of you might be thinking, wait a minute, that's even. Should I do that? No. The idea here is you're trying to make this so your substitution has this derivative. This is the derivative I want. If I change this to a tangent, I'd have a substitution of a tangent. What's the derivative of tangent?
Squares.
Is it this?
No.
If I change this to a secant, what's the derivative of a secant? This. That's why we're going to go about it this way. Okay. This, not so much. Maybe we manipulate the tangent a little bit. I don't want tan to the fourth. I want to make it look like my identity here. So I'm going to do a tan squared x squared. So the whole idea is identify what identity you're going to be using, then use it. If we have an odd power tangent, strip off a tangent and a secant. Then make your tangent into a secant. In order to do that, we've got to have our identity just right. So secant to the fourth, no, I'm going to do tan squared squared. How much is tan squared x? What is that?
Secant squared minus 1.
So we're going to have secant squared x minus 1 all squared, then a secant squared x times a secant x tangent x dx. So 10-second recap before we actually go on and do this thing. Are you guys okay with the idea that if tangent is odd, we're stripping off a secant tangent?
Yeah.
This is because we're going to work towards making a substitution. We do that by making it look like it fits the identity, doing the identity, and then doing a very simple substitution. If we do our simple substitution, u equals what?
Secant squared x.
Don't distribute now. Please don't do that. You'll have to do it later. U equals secant x. Du equal, what's du equal?
Secant x times x.
This, ladies and gentlemen, is why this works. When you strip off the secant x tangent x, you're actually stripping it off so that you can do this. So that secant x tangent x dx will equal your du. You'll change this to a u. U squared minus 1 squared. You'll change this to a u. But this whole piece, why we stripped it off, was to allow this to happen. The derivative of secant x is this. Therefore, du equals secant x tangent x dx. I want to show of hands if that made sense to you. You can follow that. What I want, it's very simple after this. What would you do?
Use FOIL and then
Distribute everything, that's right. So distribute all this crap, distribute everything, and then do your integral. Go ahead and do that at home. It'll take us maybe a minute next time we come in. Just make sure at the very end, you're going to have to substitute back in for whatever your u is. So, more torture. I mean fun. More calculus. So, what we've learned is that if we have some integrals which follow some trigonometric patterns, such as we have sines and cosines where sine is odd, or cosine is odd, or they're both odd, or they're both even, we can do stuff with that. We can work with them with following the patterns that I've given you earlier in this section. We're also moving on to what happens when we have tangents and secants. Of course, we use sine and cosine together because the derivative of one gives you the other. That's why they work. We use tangent and secant together because the derivative of one kind of gives you the other. They're related as far as their derivatives. So what that means is we can use substitutions a lot of the time if we do a little manipulation. Same thing worked with cotangent and cosecant. So here's the ideas. If you have a power of tangent or cotangent that is odd, we're going to keep a secant tangent, or likewise a cosecant cotangent, and use tangent squared equals secant squared minus 1, or cotangent squared equals cosecant squared minus 1. Do you guys see the similarity between the cos and the other functions? It's very similar. Again, the idea is this. You're stripping off a piece because you're going to be doing a substitution. So basically we're stripping off the derivative of what we're trying to get in our integral. So if we strip off, look at this, if we strip off a secant tangent, we better be substituting and making everything else in the integral a secant. Does that make sense? I'll say that again, because some of you guys weren't really listening here. If we're stripping off a secant tangent, everything else in our integral better change to a secant because the derivative of secant is secant tangent. This is what we're doing, we're stripping off the derivative. If we strip off a secant squared, if we keep that one, then everything else in our integral better be changing to what? Tangent, because the derivative of tangent is secant squared. So we're kind of taking a piece of this away of our integral, just stripping off a little bit. That way we can make a substitution that allows us to do our integral, just a basic u substitution. I want to try one more with tangent and secant, show you what that idea is like. I think last time we did one where tangent was odd. I haven't shown you one where secant is even, so we're going to do that. So here we go. Let's suppose we have an integral from 0 to pi over 4 of the square root of tan x times secant to the 6th power of x. Secant x to the 6th power. Let's see if this follows our one of our patterns. See if it fits. So what would this fit as? Would this fit as sine and cosine? Of course not. We don't even have those. As far as tangent and secant goes, what does this fit? Is tangent odd or is secant even? Which one? It does, I don't care if they're both even. We have one or the other. Either tangent's got to be odd for us or secant's got to be even. Which one do we have? Okay, so we don't fall up here. We're falling right here. The power of secant is even. No problem. Well, then we can do this. What are we supposed to do if the power of secant is even? We're going to strip off a secant squared. So basically, here's what has to happen with this. If you fit this pattern, we're going to strip off a secant squared. So this is going to become secant to the 4th power. You with me? The reason why this works so nice is because if this is even, I can strip off that secant squared, and I have something that can be raised such that I have secant to the 2nd power in there. Then I can use my identity, change everything into tangents, and make my substitution. So check this out. We're going to follow my ideas here. We'll have 0 to the power of 4. Not really any calculus happening. We're fitting this to our pattern. We're making this stuff work. We'll have tangent to the 1/2 power. We'll have secant. Tell me what I should have. Secant to the 4th. Very good. Times what? This is what I mean by stripping off a secant squared. We're taking this, well, is that still secant to the 6th? Of course it is. I'm stripping this off. Here's why, if you didn't catch it the first time, I know it's kind of out there when I'm just talking it through, but in the example, hopefully you see this. Because this was even, when I strip off that secant squared, it's still even. Does that make sense? That means I can write this as secant squared to some power. If I can write this as secant squared to some power, I can use this identity to change everything into tangents. This is the idea. If I have this tangent, I'm good. If I can change this to tangent, I'm good, because then the substitution, hey, what's a derivative of tangent?
Secant squared.
That's why we strip that off. So the idea is strip off a piece, use the rest of it to change it into whatever this one is, the other trigonometric function. So if I have tangent and secant, and I have a secant squared, I need to change this into tangent so that my substitution will actually work. Does that make sense? You wouldn't strip this off and then do something with tangent. That'd be silly. Because the derivative of secant is not the secant squared. The derivative of tangent is secant squared. So, even, good deal. We'll strip off a secant squared, it's still even. That's the point here. If it's still even, then what we can do is keep the tangent to the 1/2 power. That's great. Secant to the 4th? No. How are we going to write secant to the 4th power? What do you think?
Secant squared to second power.
Perfect. And we'll keep this exactly the way it is. I want to know how many people understand why I'm writing this as secant squared to the second. How many people understand that? Why? What's that going to allow me to do?
2 1 plus 3 squared.
Yeah, that's right. We're going to use our identity. So this one, do I want to change that? This one, do I want to change that? This one. No, this is going to allow me to make that substitution. Do I want to change this one? Oh, yeah. 0 to the power of 4, we're going to have tan x to the 1/2. In here, well, this is why we did this. Because this was still even, I can write this as secant squared squared. It's our secant squared, which we want, because we're going to do that change here. We're going to use this identity, and it still raised to some power. That's fine, we can deal with that. But I had to have a secant squared to be able to do this, to change everything into tangent. So this becomes 1 plus tangent x, like that?
Squared.
All of it squared. Let's see if that makes sense to you. Even? Cool, strip one off. It's still even, that's why we did this. If it's still even, I can write this as secant squared to some power. If that was to the 6th power, that wouldn't be a problem, that would just be a 3. If that was an 8th power, no problem, that would be just a 4. The idea is if this is even, I can strip it off, I still have something that's even, which allows me to do this idea. Once I have this secant squared, now I get to use my identity and change everything into tangent except for this guy, because I want to use this thing for my substitution. You have to have the derivative of whatever you're going to substitute. That's the basics of U substitution is the derivative has to be there. So if we're trying to change everything into tangent, we got to have a secant squared, otherwise our substitution will not work. Show of hands if you feel okay with what we've done so far. Cool. Now, should I distribute right now, or should I do our substitution right now? I would. You can distribute, but there's lots of other stuff, right? So if we change everything to U now, it'll be a little bit easier. So right now we're going to do our substitution. Can you please tell me, and I'll make a little area here for this, what is our substitution going to be? Then du equals secant squared x dx. This is why we had to have this. That's why this whole thing works. So now this part is equal to du. That's brilliant. One more thing I'd recommend to you right now is if you have definite integrals, which we do here, sometimes it's really nice to change your bounds. So I would do that if this was my problem. I'd be changing bounds right now, which I'm going to do. So changing bounds, I'm going to look over here. When x, and this is how I show it, I say when x is power over 4, then u is whatever. And when x is 0, then u is whatever we get. So when we do it next to our substitution, it makes a lot of sense to do that. If x is pi over 4, can you tell me what's tangent of pi over 4?
1.
Then u is 1. Right there, that's already a little bit nicer. When x is 0, how much is tangent of 0? Now what happens is calculus 1 stuff, but I want to make sure you get it. Now that we've changed bounds, when we get down to the integral, will we be resubstituting tan x for u?
No.
No, you changed bounds, you don't need to do that. That's why I do it now. So let's see what happens. Why don't you tell me, bless you. Don't tell me bless you, I said bless you to him. But you tell me, I love to be blessed. Bless you too. You tell me what I'm going to write. What's my integral now?
1 to 0 to 1.
Which one? 1 to 0 or 0 to 1?
1's on top, 0 to 1.
So 0 to 1. 0 to 1. Okay, what's inside?
U squared.
U to the what?
1/2.
Perfect, yeah, u to the 1/2, and then what?
1 plus u
U
squared,
squared and then the whole.
and then 11 squared.
We really want to make sure we don't miss any of those powers, because that would really blow this thing out of the water. So we have u to the 1/2, we got it. Tangent is u. So u to the 1/2, we've got a 1, we got a 1, we got a plus, we got a plus, we got a tangent squared, so u squared, whole thing being squared. What happens to my secant squared x dx? What is that? This has to match your variable. It does. We're good to go. Can you guys do the rest of it from here?
Yeah.
Go for it. Do your simple integral. You're going to be distributing a lot, of course, and then evaluate it. Let's see if you guys get to work on it on your own. Let's see if you guys get the same thing I get. Let's see, I think 2, 4 halves, 1 half, that's it. It's going to be 8 halves, 9 halves. Let me get a work check from you. Did you distribute the same that I did? You get the same thing I did?
Yes.
Good. Fractions, use your calculator if you have to. I hope that you don't. But make sure your fractions are correct. Keep on working. Are your fractions right? You got 1 half, 5 halves, 9 halves? I hope. You know what the hard part? The hard part is really getting down to here, right? Is using this stuff. This I'm hoping you guys are okay with. This is old stuff. This is just distribution, making sure you know how to do fractions, adding fractions, and then doing some basic integrals. U to the 1 half, integral of u to the 1 half is u to the 3 halves over 3 halves, 2 u to the 7 halves over 7 halves, u to the 11 halves over 11 halves, and then all of these bottom denominators just move up to the numerator. So in our case, we would have 2/3 u to the 3 halves plus 4/7 u to the 7 halves plus 2/11 u to the 11 halves. 2 moves up, gets multiplied by 2, 2 moves up. No big deal. Quick hit note if you're okay with that one so far. Okay, now, this is what I was talking about earlier. I want to make sure that you get it. Do you, at this point, have to substitute back in your tangent here?
Negative.
If you didn't change bounds, would you have to plug in your tangent here?
Yes.
Okay, so what are our bounds of integration where are we going to again?
0
1 and 0.
So we're going to plug in 1, we're going to plug in 0, but we're going to do it right to our u's. That makes it kind of nice. So I'm going to do this in my head because we have some fairly simple numbers. This was nice for us. If I plug in 1, 1 to any power gives you 1. So basically we get 2/3 plus 4/7 plus 2/11. If I plug in 0, I'm going to get 0 and 0 and 0, but I really want to check that and make sure you're checking that. So this will be minus 0. So essentially we just got to add up all of these fractions, which of course you can do in your head and get 328 over 231. I mean, easy.
Yeah.
Joking. Obviously I did that in my head. I didn't do that in my head. I'm not going to waste some time adding fractions right now. I had that done beforehand. So 328 over 231 is what you would get if you added up all those things together. Show of hands, feel okay with this one. I'm not going to waste time doing the basic stuff. This is really it, right? This is the stuff you guys should know already. So hopefully we're okay. Are we okay? You want to do one more? I don't think we've done a cotangent, cosecant. Let's check out one of those. See how that works. Are there any questions on this before I erase it this time at all?
So you were saying that if an original problem had been like secant to the 10th, then we would just
If this was the
still
same thing with secant to the 10th, you would go about it exactly the same way.
But
The only difference is this would be a secant squared, correct? And you have secant to the 8th. This would be secant squared, and this would be a 4. The only problem with doing this is that when you get down to your u sub, you'd have to distribute a lot, because you'd have 1 plus u squared to the 4th. So you'd have to distribute all of that stuff. You have lots of terms there. So, yeah, right? So it can be done, but it's a lot of distribution.
I don't know.
More?
No.
You sure? It's doable. It's just
No, I'm just wondering if you could just split it twice and then do two.
at some point you will be distributing somewhere with this stuff. Because if you do split it, right, you'll have multiplication, and when you do your identity right here, from here to here, you get a plus. After you get a plus, you will have to distribute all that stuff. That's the idea. Okay. So last one before I give you some other ideas on this section. Let's work over here this time. Okay, so let's check our pattern out. We know one for sine and cosine. We know one now for secant and tangent. Secant and tangent work, or actually I should say it this way, cotangent and cosecant work really, really similar to tangent and secant. So the same thing that we just did with tangent and secant, we can basically do it with cotangent and cosecant. Of course, the derivative is a little bit different. So it's got a negative in there we'll have to be aware of. As long as we don't mess up that negative, it works really similar. Even the identity is pretty much the exact same thing. So it's really close. So let's check it out. Which one does this fit? Which pattern? Is this the one where power of tangent or cotangent is odd, or the one where power of secant or cosecant is even? Which one? Yeah, the cotangent's odd, so that fits this top one. It says the power of tangent or cotangent is odd. We're going to do something. What are we going to do with this? Okay, so that's what I want you to do right now. Do the first step. Don't just wait for me. Do it yourself. You know what? I'm going to need more room than that. So if cotangent is odd, you strip off cosecant, cotangent. That's the idea. You strip one of those things off. Let me see if you wrote, what did you write? What did you write down? What does cotangent become? And what else? Cosecant to the 5th or to the 4th? Then what?
Would you flip them? Just
I
to
would,
make
just
it-
because I'm used to seeing cosecant x, cotangent x dx. I would do that, because that's the way it looks in my head when I do derivatives. That's the way it looks. Show of hands, feel okay with that one so far. Now, I need you to understand that don't just follow this as a pattern, okay? Really understand the process. The idea here is that this is supposed to be a derivative of something. Is this the derivative? Think about this when you're doing these problems. Is this the derivative of cotangent, or is this the derivative of cosecant? This is the derivative of cosecant. You with me? What that means is that I want all of this to become cosecant. Am I going to change the cosecant? No. Am I going to change the cotangent? That's why it's written this way for you. Use cotangent with this identity right here. Make it into cosecant. You're stripping off these pieces as a derivative. So you want to change everything else so that when you do the substitution, the derivative exists. If you do this and you start using an identity on cosecant and change it to cotangent, the derivative of cotangent is not cosecant cotangent. It would be, using this one, it would be, the derivative of cotangent would be the cosecant squared. So we couldn't do it that way. So again, the idea is when we're stripping it off, we're actually getting a derivative here. Change everything else to the trigonometric function that gives you this derivative. Is that clear? So, change cosecant? No. The derivative of cosecant is this. Change cotangent? Yes. So in our case, well, probably got to write it a little bit different. Cotangent to the fourth is not our identity. How can I rewrite that, please? Yeah. I don't want to change cosecants. Those are great for us. That's going to give us our substitution in just a second. So we write it so that we can actually use our identity. Our identity says if we have cotangent squared, that's the same thing as cosecant squared minus 1 squared. Believe it or not, we're almost done. Almost. Ladies and gentlemen, you okay so far? I want to know if you understand the reasoning behind what we're doing here. We're trying to get all of these to be cosecant because this is the derivative of cosecant. So once you have that, as soon as you have this down where they're all the same and the derivative is right here, what should you be doing? That's like the definition of when to use a U substitution, is when you have one piece that if you take it out with the substitution, and you take a derivative and the derivative is in there, it'll work. Now here's the deal, you do got to be pretty good about your derivatives of these things. We don't use derivative of cosecant a lot, but you still got to know it. Derivative of secant is positive secant tangent. Derivative of cosecant is negative cosecant cotangent. Let's switch over that negative. So negative du equals cosecant x cotangent x dx. And now this is exactly what we have here. And that'll let us do our substitution. I'm going to move up here. Can you please tell me what this integral will look like after I do all of this substitution? Integral of, what's this become?
U squared minus 1
And?
U to the fourth.
Oh, good. U to the fourth. And?
Negative u.
Good. So this is u squared minus 1 squared. Cool. We got u to the fourth power, no problem. This whole thing is equal to negative du. Do not forget about that negative. That's a big deal. So negative du, and now we'll just do a simple integral. Tell me some things that you're going to do here. Negative out front. Very good. What else? You're going to have to distribute. So negative comes out front. If we distribute, we got u to the fourth minus 2u squared plus 1. If I did it right, did I do it right?
Yeah.
Okay. Times u to the fourth. Now what? Do it again. Negative integral u to the 8th minus 2u to the 6th plus u to the 4th du. Can you guys do that integral?
Yeah.
A piece of cake. Negative, just don't forget that you either need to distribute the negative now while you're doing this, or have it out front because it will distribute eventually. 1/9 u to the 9th minus 1/3 of, no, I made a mistake, sorry. 2/7 u to the 7th. 1/5 u to the 5th. And lastly, tell me some other things that we're going to do here, please.
Substitute that.
We do have to substitute, so we don't want, I don't want u's. We start with x's. You better give me some x's.
And then distribute the negative.
And then distribute negative. So I'm going to do all those steps at once. We're going to have negative 1/9. U becomes cosecant to the 9th power of x. We're going to have plus, because we're distributing the negative, 2/7 cosecant to the 7th power of x. plus 1/5 cosecant to the 5th power of x, and finally, plus
C.
Yay! That means we're done.
You don't
I
want
like
that
that plus c.
But you don't want to factor out cosecant 5x and 1/9.
1/5 should be negative.
Oh yeah, you're right. I'm sorry, I missed that. Yeah, good catch. That should be negative. You can factor this if you want to. That's fine. I'm trying to get you to get the basic idea of getting down to here. Once you get to here, really, we should know how to do that, right? So if you get down to here and go, I want to factor that, go ahead and factor it. You want to factor some fractions? Factor some fractions. I don't really care. I want to make sure that you are good. This is really what I'm trying to teach you is up to this point. This stuff should be your basics after that. And show of hands if you feel okay with this one. Okay, those are the basic three. If we have sines and cosines, you have patterns for that. If you have secants and tangents, now you have patterns for that. If you have cosecants and cotangents, no problem. What happens if they don't fit those patterns? We're going to talk about that right now.
Like if the cotangent, you had one more cotangent in that last problem.
Yeah, some of them can't be done. I mean, some of them, there's no real good way to do them. Some of them, like I'm going to show you, the only way around doing this, like this one. Like if I were to give you that. If it fits the patterns I've given you, for goodness sakes, use the patterns and do them, okay? If it doesn't fit exactly, sometimes we can change it so that it fits a good pattern. Sometimes we can't. If it doesn't fit any pattern at all, like this one, does that fit anything? It's got secants and tangents, right? But they're not multiplied together, one's being divided. This doesn't count. This is more like tangent and, that's actually a cosine, if you move that to the numerator. That's tangent and cosine. So that's really not exactly what we're looking at. So one big hint for you is if it doesn't fit the pattern, if it doesn't fit. So first thing, you don't do this first, okay? Check the pattern first. If there's sines and cosines, you can work with it. You can work with any sines and cosines that I've given you. If there's secant and tangent and it fits so that either tangent's odd or secant's even, you can do it. If you have cotangent and cosecant where cotangent's odd or cosecant is even, you can do it. If it doesn't fit those things, then one thing you try, after you check that, see if you can change it to sines and cosines using those identities, and then see if it'll work. So let's try to change it. So the note that you probably should write down is, if it doesn't fit the pattern, try changing it to sines and cosines. That's if, though. So for others not covered, try converting to sine and cosine. So let me show you some ideas that I would do if I was looking at this problem. The first thing I would do is I'd look for any identities that I could just nail right off the bat. Now this one's pretty close, but that's not an identity. 1 plus tangent squared would be an identity. That would be easy, because 1 plus tangent squared would be secant squared would give you 1, you'd get x. Hey, that'd be nice. We're not that lucky, okay? So that's not an identity. Don't create your own identity. Some of us like to do that in this class. Instead, work with this thing with identities that you do know, or if you don't, try to break pieces apart. So first thing I'd say is, I don't really like secant squared. Secant squared isn't cosine. So one thing I would try is, I would split up this integral into 1 over secant squared x minus tangent squared x over secant squared x. The reason I'm doing that is because I know that 1 over secant squared x is actually the same as what? Cosine squared. Remember, convert to sines and cosines. That's one way we can do it. So then this becomes cosine squared x. And let's take a look at what this actually is. What this actually would become This is tan squared x times cosine squared x. Believe it? This is cosine squared x. That's what that is. So 1 over secant squared is cosine squared. Understood? Well, what's tangent?
Sine over cosine.
So tangent squared is sine squared x over cosine squared x times cosine squared x. What happens here? That's fantastic. So just by doing a little bit of a change here, by pulling those fractions apart, and by using our identities for what 1 over secant squared is, for what tangent is, what 1 over secant squared is, we can simplify this fraction from this nasty thing to this really nice thing. I need to show of hands if you're okay with that one. Hey, have we done any calculus right now?
Not yet.
This is trigonometry, purely trigonometry. In fact, the next step is going to be trigonometry because this is kind of awesome. There's an identity, and if you want to look it up right now, you can look it up. This is actually an identity. Do you know what it is?
-1.
Please don't say 1 or -1.
Sine 2.
This would be 1. That would be 1. This is not -1. That's not the way that this stuff works. No, it's not. It's not. But if you want to look it up, go ahead and look it up.
I think I know what it is.
Okay, Rob.
Cosine 2x.
Perfect. Does it help to know your trig identities? Because if you didn't know that, look at this. You know how to do cosine to evens, don't you? You know how to do that. You'd have to do this one. You have to do this one independently, and then you'd have to put them all together. But if we know our identity, we go, oh, hey, look at it. That's cosine. Can you do this? That's now a piece of cake. This would be like, I would do the U sub in my head. I don't write out the U subs for a lot of these trig ones because they're so easy and and we do so many of them, especially like you found out in your last homework, or this homework, I'm sorry, when you have like cosine squared of 2x, well then you're going to be getting 1/2 1 plus cosine of 4x. That angle is going to change. If you do a U sub right off the bat with that, you're going to have like 8 U subs per problem. That is going to suck. So I just do them in my head. I go, okay, what's the integral of cosine? It's positive sine. Whatever's in my hand, I don't change, but I divide by the derivative of whatever's in my hand. It's like the opposite of a chain rule. Instead of multiplying by derivative, you just divide by derivative, and that works. Does that make sense to you?
That's doing U substitution in your head.
That's a U sub in my head. I'm doing U equals 2x, right?
Yeah.
Derivative is 2. Dx equals du over 2. That's where the over 2 is coming from. Plus c lets me know I'm done. And I'm done. Show of hands if you feel okay with that one. Identities are nice. Try to use those. And the ones that don't follow the pattern, you are going to have to change the sine and cosine for most of them. Once you do that, please, for your sake, look at some identities and try to work with them. Just follow the correct identities down and you'll be good to go. Can we move on?
Yeah.
Now, there's one more thing that we haven't talked about that I'm going to give you one example with, and we'll call it a day. Have you noticed in all of these patterns that these angles are always the same? Have you ever wondered what if the angles aren't the same? Have you wondered that? We're going to do one like that right now. So what happens where the angles of sine and cosine are different? So for integrals, where sine and cosine have different angles, try using these three identities. Again, of course, with trigonometry, we almost always go back to identities at some point. Even with our basic patterns, we're using identities. Same thing happens here. If you got integrals of two different angles, this is what you do. There's three cases. There's where you have two sines, where you have a sine and a cosine, or where they have two cosines. There's only three cases. So let's suppose I have sine times sine, where the angles are, different. Where the angles are different. You know what, I'm going to need more room. Write that down, but I'm going to write it just over here a little bit. Or where we have a sine and a cosine, where the angles are different. Or lastly, where we have a cosine and a cosine, where the angles are different. Here's some identities. I don't know if you've ever seen these before. You may have, I'm not sure. You probably have somewhere, but we don't use them very often. Here they are. So if you have sine of something times sine of something where your somethings are different. Here's how I do it. Probably something you're going to want to write down and have next to you when you're doing your homework. At least I would.
Problem 40.
Bless you. Thank you. You're not allergic to this, are you? Okay, goodness. I gotta make sure I'm right too, so let's look at that. 1/2 cosine, yes, minus cosine, okay, good. And that one. Cool, and that one. Okay, write them all down, look up here when you're done, that way I can talk at you, we're gonna do an example here. So continue writing, then let me know that you're done. And then we will do an example. All right, have you written all down?
Yeah.
You get this perfectly right? Sine for sine, pluses and minuses, sine for sine as well? Okay, good. So let's check this out. If I hadn't told you this, could you do that problem? Well, you might. You might be able to change this, cosine 2x. I'm sure there's an identity for that one. But we have an identity that will change this directly and make it a lot quicker, a lot easier for us. So let's check it out. We got sine x, cosine 2x. Do you see what I mean about different angles?
Yeah.
So what this says is this would be our mx. It's just 1x. This would, oh wait, which one are we at? Top one, middle one, bottom one. So this is our 1x, this is our 2x. It just basically says, look at this angle, do this with it. So when we're doing this with it, we still maintain our bounds of integration. We're just going to do our identity here. So what's the first thing that we're going to do? 1/2's got to be there. What are we ultimately going to do with that 1/2? No, we're not going to distribute it.
Oh.
We're going to pull it out. Okay, so I'm going to draw my bracket here. Let's change this using this identity. Tell me the first thing I'm going to write inside of my bracket. Sine of what?
X.
Good, it just says this angle minus this angle.
Oh, X
X minus, not 2x minus that, x minus 2x. Okay, what else? There's a plus holding those together, and then another sine, and then what?
X plus 2x.
Perfect. Don't forget your dx's. Let's simplify it a little bit. What do we got here?
sine negative X.
Still 0 to the pi over 2. We're not going to change those yet. We haven't done any substitutions, so we still have that. What now?
Well, 1/2.
1/2 is out front. Okay, what now?
Sine of
Wait, sine of what?
Negative
X.
Possibly.
Sine of, combine of negative x. You okay with sine of negative x?
Sure, it's equal to negative sine x.
Are you, first, I want to make, I get some weird looks on that one, like, what are you doing? What's x minus 2x? Okay, you can do this stuff, okay? Just combine them. They're inside the parentheses. X plus 2x is, oh, good, okay. Some of you are thinking so hard, you're missing the easy stuff. That happens a lot in this class. Quick head nod if you're okay with that so far. The reason why this exists is so that you can actually combine the angles, all right? You would, this looks crazy. I mean, this, yeah, combine them. Negative x and now, this is an issue because we don't want to end with the sine of a negative x. We want sine of x. We want to end with that, or whatever we have here. So, I mean, cosine, actually, you need an identity for this one. Sine of negative x equals, good, it's an odd function. So when we do this, we all right, this is not a problem. This will be 1/2 0 to pi over 2 of negative sine of x plus sine of 3x dx. Let me ask you something. Can you do this integral? That's a piece of cake. It's not cosine. What's the, can you do this integral? It's a piece of cake too. No problems. Let's do the integrals. What's the integral of, and let me write this out here. One half's going to be there, no problem. Let's create a bracket here so we don't lose anything. What's the integral of sine x? Can you tell me?
Negative cosine.
Negative cosine. So, watch carefully. I'm going to do some math in my head here. If this gives you negative cosine, this gives you cosine x. This would give you integral of sine x is negative cosine. So negative, integral of negative sine x is positive cosine x. Show if you feel okay with that one.
Double negative.
Okay, double negative. Two wrongs make a right here. So let's do the next one. What's this going to give you?
Negative cosine 3x times 3x.
Negative cosine 3x. Okay, so instead of plus, I'm going to have minus cosine 3x
Oh, divide by 3.
over 3. That's a little use of in your head, the over 3. So when you're doing these, do the integral, no problem. Negative, so minus cosine. Negative, so minus cosine 3x over the derivative of 3. Show if you feel okay with that one. Good deal. Now what?
How you do your definite integral.
You could choose to distribute that if you really wanted to. You don't have to. You can wait till the very end. I would. I like dealing with this and that separately. You could actually divide out a 1/3 if you want. You could do divide out a 1/3. This would become 3 cosine x minus cosine 3x. Not a problem. That would get rid of that fraction in there. So whatever you want to do as far as this goes, this is just algebra. Just plugging in some numbers and doing it. So I'll leave the 1/2. Just remember that in here, when you evaluate, you'll have cosine of pi over 2 minus cosine of 3 times pi over 2. That'll give you nice numbers. Should I bother to plug in 0?
Yes.
For heaven's sakes, yes.
Yeah.
Minus cosine of 0 minus cosine of 3 times 0
What about the 1/2?
over 3.
Oh, it's still in bracket.
I don't think I forgot anything, but you let me know if I have. Have I forgot anything?
No.
Okay, so we got the 1/2, we get the 1/2. Big old bracket, you need the big old bracket. This is the evaluation of pi over 2. So cosine pi over 2, cosine 3 times pi over 2 over 3. Are you guys okay with that one? Minus, no problem because you subtract with this, cosine of 0 minus cosine of 3 times 0 over 3. Let's work it out. So this will give us 1/2. Big bracket, don't lose things here. What's cosine of pi over 2?
0.
How about cosine of cosine of 3 pi over 2? My bad. 0. 0. 0 over 3. Big difference. Cosine of 1. Oh, shoot.
Cosine of 0.
Cosine of 0 is 1. How about, this is also cosine of 0.
1.
Minus 1/3.
Oh, 1.
Don't forget about the 3. This is 1/3. You okay? If you forget about the 3, this whole thing goes to 0. You go, wait a minute, that doesn't make sense. I can have an area that's 0. You can. Complex analysis doesn't matter. What happens here? So this is 0. 1/2 0 minus
1/2.
You did right. I got negative 1/3. Did you get negative 1/3?
Yeah.
We are done. Did that make sense to you guys?
Yeah.
Okay.